Have you ever wondered why the speed of light is the ultimate limit of the universe? Why can't a car, spaceship, or even your own body, no matter how much energy we have, ever reach or exceed it? The answer lies in some of those mind-bending laws of physics, where time, space, and energy all behave in ways that seem to defy common sense today. Today, we're exploring why objects' mass can never hit the speed of light, and what fascinating rules the universe follows to make this impossible. Imagine a 4,000-pound car is rolling down a road at 20 miles per hour. It is moving, which means it has momentum. The product of mass and velocity. Momentum is one of the key ideas in physics. And here's something cool. It can't just appear or vanish. It's a conserved quantity, meaning the total amount of momentum in a system stays in the system no matter what, unless an outside force interferes. Now, let's say you want to stop the car using a simple object, like, for example, a 20-pound dumbbell. For this to work, the dumbbell would need to be thrown at just the right speed to counteract the car's momentum. First, we translate the problem into the world and language of physics. The car's mass in the metric units is going to be about 1,814.3 kilograms and a speed of about 8.9 meters per second. The dumbbell weighs 9 kilograms, so we need to find its velocity. Using the formula for momentum conservation, mass 1 multiplied by velocity 1 equals mass 2 multiplied by velocity 2. We calculate the dumbbell would need to be moving at a staggering 1,794.1 meters per second, or about 4,000 miles per hour, to stop the car completely. If you could throw a dumbbell at this incredibly fast speed and hit the car, their momentum would cancel out, leaving both objects at rest. This is the principle of conservation for momentum. Okay, now let's look into what this means and how the rules apply when we're moving close to the speed of light. The speed of light is approximately 300 millimeters per second, represented by the constant c. This is the fastest anything can travel in the universe. But why? To understand this, we look into Einstein's two postulates of special relativity. Number one states that the laws of physics are the same for all observers, regardless of their motion, also known as Galileo's dictum. The second postulate states that the speed of light is a vacuum, is a constant at c, and does not change based on the motion of the source or the observer. The second rule is key. It's what makes the light speed unique and creates the mind-bending effects of relativity. The slowing of time is known as time dilation, as described by the Lorentz factor, or also known as gamma, which equals 1 over the square root of 1 minus velocity squared divided by c squared. At the low velocities, gamma is nearly 1, and time flows normally. But as v approaches c, the denominator shrinks, making gamma grow infinitely large. For example, at 50% the speed of light, gamma is 1.15. At 90% of the speed of light, gamma is about 2.29. At 99.9 the speed of light, gamma is 22.37. And finally, at 99.999999999% the speed of light, gamma is an astounding 707,107. This means that for moving objects, time slows dramatically compared to an observer at rest. The faster you go, the more extreme this effect becomes. But gamma doesn't just affect time, it also increases mass. As your speed gets closer to c, your effective mass grows, requiring more and more energy to accelerate further. Let's take a look at why your mass increases as well. Let's visualize the effects of relativity in an example. Imagine there are two mirrors, 300 millimeters apart. A massive particle, a photon, bounces between these mirrors, traveling at the speed of light. When the mirrors are stationary, the photon travels straight up, straight down, covering 300 million meters every second. But now, imagine the mirrors are moving sideways at 400 millimeters a second, a hypothetical speed for a visualization. From our perspective, the photon's path becomes a diagonal as it chases the 2 meters. Technically, 400 millimeters per second isn't possible, but we're going to use it to keep the numbers simple. Using the Pythagorean theorem, we can calculate how far the photon travels between the bounces. In end, it's actually traveling 500 million meters distance. So the photon is traveling 500 million meters in one bounce. But the fascinating part is the speed of light, c, cannot change. It has to be 300 million meters per second. A photon must still travel at 300 million meters per second to make this work. It's not the velocity or the distance that changes, but it's time itself that slows down. According to Einstein, space and time aren't two separate concepts, yet one existing with each other. Now, let's consider what happens when objects with mass, like a spaceship or you, approach light speed. Imagine you and your nemesis are running 95% the speed of light, fist raised, and about to collide. From your perspective, they appear in slow motion due to time dilation. But from an external point of view, you're both traveling at the same time. To you, their punch is very slow and yours is faster. You will destroy them. But when you collide, you both stop in motion because from the outside perspective, your momenta is the same because you have the same velocity and the same mass. To keep the system balanced, your mass has to increase as you're moving faster. The mass increase is also tied to gamma. As your speed approaches c, your gamma value and therefore effective mass become enormous. If you could somehow keep accelerating, your gamma would approach infinity. Infinite gamma means there's infinite mass. And to move infinite mass, you need an infinite amount of energy. But here's the catch. Energy isn't infinite. The universe has a finite resource, and no matter how much energy you pour into an object, you can never supply an infinite amount needed to reach the speed of light. Why can't anything with mass reach the speed of light? The universe's rules, time dilation, momentum, and energy conservation combine to create an unbreakable barrier. As gamma grows, time slows, mass increases, and energy requirements become infinite. This isn't just a limitation, it's a profound insight into nature of reality, where the speed of light acts as a fundamental constant shaping how we experience our time, space-time. Thanks for joining us on this journey through space-time and the speed of light. If you learned something today, make sure to hit that like button and subscribe to the Education Station for more videos like this. See you next time. This is Cody signing out.